Hi, this is Bilal, leader of Group8, and we will be covering the implementation, applications, and evaluation of support vector machines. So, for the implementation part, we'll basically discussing two scenarios here: linear classification and nonlinear classification. Support vector machines are usually used for classification and sometimes for regression, but their use case can depend on the data set that you're working on. They can classify, they can find linear boundaries as well and nonlinear boundaries as well. For the linear classification problem, we have the iris dataset because it's linearly separable. For this, we're going to import the iris dataset from scikit-learn library, and for using the support vector machines model, we'll be importing the SVM package from scikit-learn. And after loading the iris dataset as a data frame, a pandas data frame, we'll be instantiating a class of support vector classifier with a linear kernel, since we want to find a linear decision boundary. After partitioning the data into a 70% training set and a 30% test set, we will fit the model on the training data and then perform predictions on the test data. And as you can see from the classification report, we have 100% accuracy. For the nonlinear classification, we'll be using the make-moons dataset, as it is nonlinearly separable because of the crescent-shaped clusters in it. We'll be importing this from scikit-learn as well, and we will perform the same partitioning of the data. This time, when we instantiate the support vector classifier, we'll be using the RBF kernel, which is used for finding nonlinear decision boundaries. This is also the default kernel for the classifier. We'll perform the model fitting and then perform predictions on it. And as you can see, the classification report shows pretty good results.
Okay, hi. The second part is about the key application domains. It's about the test imaging by informatics. The first one is about test. SVM are commonly used in natural language processing. It's about key applications. It's about the test classification, for example, like spawn, email identification. Second, about the machine translate, for example, like Chinese to language. English. So it's about information extract. For example, the key extract phrase. The second is about the images. Image application, I think, is equal to computer vision. So image application uses ML to detect patterns, objectives, and things within images. Key applications. The first one is about imaging classification. The second is facial recognition. Third is about the imaging generation and restoration. So it's about the bioinformatics. Bioinformatics applies ML to genomic and protect data, essential for precision medicine. Key application is about the first one is about the protein classification. The second is it is about gene expression analysis. Third is about disease diagnosis. Fourth is about gene prediction. The last one is about drug discovery.
Hello, I'm Callum, and I'll take you through the strengths and weaknesses of SVMs. The most important strength is that it's effective in high dimensional spaces. This is even when you have more dimensions than the number of samples. In addition, it can be done with the right margin and maximization and regularization techniques. SVMs can generalize well on unseen data, and it handles sparse data well, meaning it's suitable for text classification tasks. And the most important is that it's highly interpretable at the 1 to 3D dimensional plane, possibly the fourth dimension as well, meaning that the visualization of the hyperplane and support vectors becomes very intuitive. However, on the flip side, if the number of features far exceeds the number of samples, then the kernel choice and regularization is necessary to avoid overfitting. And SVMs do not provide probability estimates. These are only calculated at an expensive five-fold cross-validation. And then the most important of all is that as the number of dimensions increase, the cost and complexity for additional samples grows between n squared and n cubed, meaning for 100 times more samples, you're looking at potentially 1 million times the cost, which is significantly larger than any other alternative technique.